Okay, hello everybody. So today's session is going to be all about MPI and OpenMP. So what I'm going to cover is some motivation. Why would you want to use hybrid MPI and OpenMP in your application? And then we'll look at the potential advantages. Why might you? What are the reasons why you might want to do it? What can you gain from it? And what sort of expectations you might have? And then kind of we'll look at the other side of the coin is what are the potential problems? What can go wrong? And what can you do about it? And then I'm finishing off by looking at the different possible styles of writing MPI and OpenMP. So there are different ways of writing hybrid code depending on how you where in the OpenMP program do you allow yourself to make MPI calls and how. And as part of that, we'll be looking at MPI's thread interface. So what's the motivation? Well, of course, for quite a while now, everything's been multi-core, and the sort of current trend in hardware is still for increasing core counts on chips. So we're now seeing chips with 64, 72, 96 cores on them, and then typically you have 2 chips, 2 sockets per node in a lot of HPC configurations. So you have having nodes with approaching 200 cores in them. So that's the way we build supercomputers at the moment. Use these large-scale multi-core chips. Put typically 2 of them in a node. Doesn't have to be 2, but that turns out to be the optimum number in current hardware. Typically, I mean, sometimes you'll see 4, but 2 is the most common currently. And then we connect those together with a network to make a large-scale system. So what we've been working with in HPC for quite a long time now are these distributed memory systems where each node consists of a shared memory multiprocessor. So we have from a programming point of view, we have a single address space available within every node, but separate nodes have separate address spaces. So the question is, how should we program such a machine? Well, it's perfectly fine and it works, is just to use MPI, plain old MPI across the whole system. So we can run potentially, typically 1 MPI process per hardware core. And the MPI implementation is typically optimized in such a way that communication between MPI processes on the same node is done through shared memory rather than across the network. And there's a reasonable amount of sophistication in the MPI libraries. The libraries are aware of this hierarchy in the hardware, and for example, they will use knowledge of that for implementing, say, collective communications. So if you do an MPI or reduce, for example, then typically you will get the implementation will form the sum locally on a node, do that in shared memory, and then form the sum across nodes with communications over the network. So unfortunately, at least in general, we can't use a model like OpenMP or other threading model across the whole system across more than 1 node, because that requires support for a single address space. So it's not impossible. You know, in the past, people have experimented with systems that do this kind of thing. You can do it in software. You can create a single address space across multiple nodes, and you essentially manage everything with moving operating system pages around. It's doable, but it's pretty inefficient. You end up with far more communication than the underlying program or algorithm really needs, and it's never been successful. You know, it's never been demonstrated very successfully in terms of efficiency. You can also do it in hardware, so you can build larger scale NUMA systems. So that's also been done in the past. Is to build non-uniform memory access distributed shared memory systems with, in the past maybe a few hundred nodes is possible. And you do eventually, even with that, so the hardware is expensive to implement. You need lots of some special cache coherency mechanisms to implement it effectively, and eventually even if you do that, you do eventually run out of scalability at some point. So that's kind of why we end up with the sort of system that we have, which is a distributed memory system with shared memory nodes. So potentially we could use OpenMP or some other threading model within a node and use MPI still to communicate between nodes. And the question is there any advantage to that? And so the short answer is yes, maybe. Okay, so that's what we're going to look into. So we have to really consider, think about our expectations here, and and think what can we potentially achieve and when. So in general, mixing MPI and OpenMP is not going to really improve performance, and may actually be worse if we're in the regime where the MPI application is scaling well. Okay, so if the MPI application is, if we're working with a number of nodes and a problem size where the MPI application is scaling perfectly happily and the parallel overheads are relatively small, then probably we're not going to gain anything very much from adding OpenMP. The benefits tend to come where the MPI scalability, so that's could be either in execution time or possibly also in memory usage, starts to run out. And then really what our expectation is hopefully that MPI plus OpenMP may extend our scalability to larger core counts than what we can achieve with MPI alone. So if you look at hybrid applications and you sort of plot their performance, so in whatever suitable units are, some either it's just like sort of 1 over the execution time, or in some other suitable metric for the application, like time steps per second, solutions per second, simulated nanoseconds per second, whatever. So plot some performance metric where high is good against the number of cores that we use. Then so typically what you find for parallel applications is that for small numbers of cores they will scale well, maybe almost linearly, and then eventually the scalability starts to drop off, and we get a pointer. And so at some point the scalability will peak, and then adding more cores will actually make the performance go down again. Because at this point you've run out of scalability, and the whole computation is completely dominated by parallel overheads, which can be of different types. They could just be communication overheads. but they could also be load balance as well. For example, might also at some point kill your scalability. So kind of what we might hope for by going from pure MPI to MPI plus OpenMP is not really to improve the performance in the good scaling regime. So down at the bottom left here, small numbers of cores where our scaling is linear. So what we might actually typically find is that the performance of the MPI plus OpenMP is actually a bit worse. Maybe not very much, but slightly worse in this regime. But the scalability extends better. Okay, so that you can achieve higher performance at the kind of core count where the MPI scalability is starting to run out. So typically, you might run your pure MPI application in. You might choose to run your application in kind of this regime here and get this sort of performance. Whereas with hybrid code, you might choose to say, okay, I'm going to run so maybe up here somewhere. So I use more cores, but ultimately get better performance. Okay, any questions so far? Okay, so let's move on and think about what are the potential advantages of using MPI and OpenMP together. So what kind of problems can it potentially solve? And so you can think of maybe a list of them, which might look something like this. So the first one might be simply just reducing memory usage. Okay, really sort of nothing really much to do with performance directly, but just being able to fit a certain problem size into a certain number of nodes. Another thing you might think about is, well, can I use it to exploit some additional levels of parallelism? Can I use it to reduce load imbalance? Can I avoid some replicated computations? Or can I reduce the communication costs? So let's have a look at each of these. Okay. So first of all, reducing memory usage. So some MPI codes will use some sort of replicated data strategy for some data structures. So you end up with all the MPI processing having a copy of some major data structure. Even if you do very classical domain decomposition in MPI, then there is still some data replication going on by having halo cells or ghost cells. So you're bound at the boundaries between your domains. Then you have data which is replicated on neighboring processes. Something else which can also be an important consumer of memory is MPI itself. So MPI typically needs to allocate memory inside the MPI library for message buffers, and those can end up consuming significant amounts of memory. So if we have replicated data, then if we have a pure MPI code, then we need a copy of that thing for every process and therefore for every core typically. Whereas we might, because threads naturally share memory, a mixed MPI and OpenMP code could potentially, if you go to the other extreme, only require one copy per node. and then the data structure can be shared by multiple threads within a process. And this, also helps to. This also may also help to reduce the amount of internal memory consumption by MPI as well, because it can get away with fewer buffers if messages are being sent via shared memory inside the node. They still probably need some buffers, but you can end up with one copy instead of one shared copy rather than one copy for every process and so on. So it can actually reduce MPI's internal memory consumption as well. Okay. So I mean, this is kind of an old statement, but I think it still holds. Okay, if you look at supercomputer design, you say, how much memory do I have per core, and that's remained more or less constant for quite a long time. So we often typically end up with a few gigabytes, 2-4 gigabytes of memory per core is fairly typical. I mean, that's not a technology limitation. It's perfectly possible to put a lot more memory inside nodes. It's really an economics decision, because you have to, well, the memory itself is expensive, and then you also have to power and cool it. So it's really a decision about finding a sensible economic solution as to how much memory you give per node and per core, and sort of kind of the accepted norm really, and what works for the majority, typically works for the majority of applications is to have a few gigabytes per core. Okay. So just have to think about, what's the effect of, what's the effect of the domain size on Halo storage? Suppose I do, classical domain decomposition, then, so typically if I try to do strong scaling or something that's not genuinely weak scaling, then, using more processors, using more cores is going to imply, for a fixed problem size, implies having a smaller domain size per processor. And although the total amount of Halo data does decrease as your local domain size decreases, it eventually does start to occupy a significant fraction of the storage. And that's made even worse if you have deep halos, for example. So instead of having one layer of Halo cells or ghost cells, you might some applications might choose to have 2 or 3 Halo cell layers, or you can have strange applications like QCD, where you're operating in more than 3 physical dimensions. So you just do some quick sums. So suppose we have a local domain size. We do 3D decompositions. Suppose our local domain size is 50 cubed grid points or cells or whatever they are, and we have a 1 deep Halo. Then so the Halo storage is then sort of 52 cubed minus 50 cubed, and that accounts for about 11% of the memory consumption. So then if you just do the same calculation and you say, okay, let's use more cores, so shrink the local domain size down to 20 cubed, then we have 25% of our storage is consumed with Halo data. And if we go right down to say 10 cubed, then we're approaching using half our memory just to store Halo data. So simply doing that may be, maybe a very strong motivation for using MPI and OpenMP is simply just to reduce the memory requirements and be able to fit larger problems into a given number of nodes. So the alternative would be simply underpopulating the nodes, so using fewer MPI processors per core. So the other way of looking at it is to say, well, if you're forced into underpopulating, then you are leaving some cores idle and not using their compute capability. Then perhaps at least you can recover at least some of that lost performance by running multiple threads per process and using all the cores. So let's move on now and look at potential reasons why you might gain performance. And the first of these is the ability to exploit additional levels of parallelism. So, some MPI codes, for certain, for problems which are of scientific interest, don't scale beyond a certain core count because they run out of available parallelism at the top level, the level which the MPI implementation is exploiting. But there might well be some additional lower levels of parallelism that could also potentially be exploited. And in principle, you could also do that. You could also do that with MPI. There's no, no in principle reason why not. But in practice, that can be hard. Okay, for various reasons, because the lower level of parallelism may be more awkward to implement in distributed memory. So, for example, it might be hard to load balance, or it might imply irregular or runtime determined communication patterns, which are really painful and difficult to implement in MPI. It's essentially nothing's impossible, but it may be just really challenging from a programming point of view to exploit those sort of different types of parallelism. But perhaps more relevantly or more commonly, it may just be simply hard to work around design decisions that have been made for the original MPI version. So exploiting additional levels of parallelism might imply very heavy and extensive refactoring of the code, which you might decide is not worth it or infeasible in a reasonable time, or you don't have the programmer resources to undertake it. So for those kind of practical reasons, it might end up being easier to exploit those additional levels of parallelism using OpenMP threads. From a software engineering point of view, we can take a reasonably incremental, so even sort of loop by loop approach to adding OpenMP. That might not be performance optimal, but it at least keeps our development cost and development time to a minimum. So obviously, the OpenMP parallelism can't extend beyond a single node, but that might well be enough. So again, we're just seeing the way we're getting more performance out of hardware these days. GPUs aside, for CPU-based systems, the only really way we're getting more performance is not by having more nodes, but by having more cores per node. So that means potentially we have more hardware resources available to exploit parallelism in the shared memory context. So second reason why you might benefit from MPI and OpenMP is avoiding replicated computation. So some MPI codes do replicate some computation because it's cheaper or more convenient, easier to program than computing something on one process and communicating the result. And sometimes here, for example, we can we trade off duplicated computation in halo regions with communication. Okay, so there are methods where you can you can do more computation and less communication instead. And using mixed MPI and OpenMP may help reduce that. So, for example, because you make your domains bigger, you have less data in halo regions, and therefore there's less replicated computation to do. The next possible reason is reducing load imbalance. So if we have problems which are not naturally well load balanced, then load balancing between MPI processes can be hard. We need to be able to transfer both computational tasks and their associated data from overloaded to underloaded MPI processes. So that can be difficult, and so transferring small tasks may not be beneficial. Okay, so the cost of moving the data may outweigh the benefits that you get from better load imbalance. If you want to scale to very large problem size, very large core counts, or so really very large MPI process counts is what really matters here, then having a global view of the loads on every MPI process may not scale well. So it's maybe fine if you've got 1,000 MPI processes to communicate for every process to communicate its current load to the master process, who calculates some redistribution and tells every other process what to do, how to redistribute their load. And that might work okay for 1,000 processes, but as you go to 10,000 processes, 100,000 MPI processes, then that might that's a sequential bottleneck which can limit the scalability. So you might have to then restricted yourself to some some local load balancing scheme rather than a global one. So for example, what's often typically done is that you have to restrict yourself to transferring loads only between neighboring MPI processes. So if you have some sort of domain decomposition, then you only consider transferring load from overloaded processes to its immediate neighbors, its immediate physical neighbors, rather than redistributing across the entire MPI communicator. So basically, it's just hard. Okay, it's difficult to implement, difficult to make it scale. And on the other hand, load balancing between threads is typically much easier because, in principle, we only need to transfer the tasks and not the data. Of course, moving tasks, between threads means they get executed on different cores, so that might imply some data movement through the cache coherency mechanism. But the overheads are typically lower. Okay, so and it's possible to do much finer grained load balancing with threads than it is with MPI processes typically. And it's easier for, at least if you're just considering balancing between different threads, to essentially have a global view and to do dynamic load balancing. So if you think that OpenMP has built-in dynamic load balancing through dynamic schedule, guided schedule, using tasks and so on. Whereas implementing that kind of thing in MPI is quite hard. So what does that mean? Well, it means that we're not going to completely get rid of our MPI load balancing problem, but for applications that do have load balancing problems, keeping the number of MPI processes as small as we can be an advantage. And we can do cutting down the number of MPI processes, say by an order of magnitude, might make the MPI load balancing a lot easier, a lot more scalable, and then we can take care of load balancing inside an MPI process by using the OpenMP type mechanisms for loop scheduling or tasks or something like that. And then the final one is reducing communication costs. So again, we have to kind of temper our expectations a bit here, because it's very natural to suppose that if communicating data inside a node is going to be faster between OpenMP threads than it is between MPI processes inside the same node, because there's we don't need to do any copying into buffers. There's no intermediate copies need to be made, which MPI typically does. And there's no library call overheads going on. You don't have to go through the MPI library software stack to do the communication. So in principle, that's true, but there are lots of caveats to that, which we'll come back to when we look at some of the problems. However, in some cases, again, for convenience of programming and implementation, some MPI codes actually communicate more data than is actually required. And this typically happens where the actual data dependencies are irregular or themselves data dependent. Okay, so the data that you really need to communicate depends on some values of current variables, for example. I'll show an example of that in a minute. And simply just communicating everything that your neighboring process might need, rather than try and figure out exactly what it does need and communicating only that, is typically easier. And also with collective communication, in some circumstances, collective communications can be improved by using MPI plus OpenMP. In principle, the MPI implementation ought to be well optimized for these kind of clustered architectures. It's not always the case, and there are some collectives which is actually hard to do. So all-to-all V, for example, is difficult to optimize. So all-to-all V is where every process sends a different amount of data to every other process, and trying to optimize that for a hierarchical architecture is actually hard. So there can be cases where the hybrid version, the hybrid MPI plus OpenMP version, transfers less data. So, for example, if you have an all reduce where maybe every thread contributes to the sum, but only the master thread on each process actually uses the result. So then there's kind of a stage that's maybe reducing the number of stages in your communication tree pattern that's actually needed. Okay. So one example of this, and so this is basically taken from a weather forecasting code. So this is the European Centre for Medium Range Weather Forecasting. Their system is called IFS, so I think it stands for Integrated Forecast System, I think. It's the main code that they use for weather forecasting and climate simulation. And it uses a method called semi-Lagrangian advection. And what does that mean? Okay, so advection is just the process of moving stuff around in the atmosphere. Okay, so if the wind's blowing from the west, and the air is hotter to the west, then the temperature locally is going to increase. So that it's basically implementing that bit of the physics in the fluid dynamics. It's basically just moving air around. So in this kind of if you do this algorithm called semi-Lagrangian advection to do this, then the data dependency is that you only require data from neighboring grid cells in an upwind direction. So you only need the data that's coming from cells where the wind's blowing from, which kind of makes intuitive sense, but not all numerical advection schemes, actually exploit that. So to implement this MPI, then you have this problem. So you don't know what the wind field is on your neighboring processes. So, and you could communicate that, but then that would just cause you extra communication anyway. So what the MPI solution is, you communicate all the data to neighboring process that could possibly be needed, for whatever wind fields they might have at the current time. Whereas if you do this with MPI and OpenMP, then at least within a node or within an MPI process, you're only reading the data from other threads' grid points if it's actually required. And this can result in a significant reduction in the overall communication costs. So basically, the idea is look like this. Okay, so suppose this is a typically weather forecasting codes. They only do a two-dimensional decomposition across the surface of the Earth. They typically don't for reasons of the way the physics works. Weather forecasting typically does not try to exploit parallelism in the vertical dimension. So suppose so here's here are our 2D domains of the surface of the Earth, and suppose this middle process here. Suppose these red arrows represent the current wind flow direction. So the semi-Lagrangian advection scheme might only, if you work out what the actual data dependencies are, which data do I actually need to implement this, it may turn out that the green data points here, okay, so the green grid points are the ones where I actually need data from to calculate the values for the next time step. Okay. But in an MPI implementation, can't know that. Okay, so so for example, this processor up here cannot know that its neighbor doesn't actually need any of its data values. So you end up communicating, and the way this one works, it actually uses deep halos. So you can end up communicating all the purple data points as well as the green ones. So what does that look like here? You end up with communicating maybe 4 times as much data as what you really need. Whereas if these, if you think, okay, so if these domains are now were instead if they were assigned to different threads, and these all this data lives in the shared memory on a node, then the thread that's processing this domain, this part of the domain, it can simply read read the green values, and it will never read the purple ones. This kind of problem also occurs in molecular dynamics as well. You typically have an interaction distance, so you can end up, you have to communicate all the information about all the particles that are within interaction distance of your of the domain boundary, even if there's maybe even if there's nothing on the other side of it for them to interact with. So there's other types of application where you can where you end up with the same problem of communicating more data than you really need. Okay. Any questions about that? Okay, Raymond asks, when developing a program, should you start with a the non-MPI, non-OpenMP program as a baseline first? Start with your sequential program. So would you suggest you add OpenMP first or MPI first? Yeah, that's an interesting question. It's relatively uncommon to be, maybe relatively uncommon to be developing code completely from scratch like that, but it does happen. Yeah, you're probably going to want to do your MPI decomposition first, because that's much harder to implement, and you need to make a lot of changes to the code typically. Compared to using OpenMP, doing MPI is going to cause you a lot of changes to the code. You have to rethink your data structures. You have to explicitly develop all the communication patterns and so on. So I guess in most cases you're probably going to want to do the MPI first, and then add the OpenMP afterwards. But it's always good to bear in mind, when you're making design decisions, both about the original sequential version and about the MPI version, is to bear in mind that you're going to be adding OpenMP at some point, okay, and have that inform your design decisions as you go along. Of course, you might be in the other situation, and it depends. You might say, well, actually, what's my target here? Is it recognize that that the MPI implementation is going to be a lot harder than the OpenMP one? Do you want just to have a plain old OpenMP one anyway? So yeah, it will come down to individual decisions about individual bits of software, what you intend to use them for, how big you want to scale them, all this kind of thing. Okay, so let's then think, okay, so that all sounds great. There's various problems with MPI codes I can potentially solve with using MPI and OpenMP together. What are the problems? Okay. So have a look at some of these. So development and maintenance costs, portability, issues with libraries, and then what can go wrong with performance. So let's think about the sort of software engineering concerns to begin with. So in most cases, adding an extra programming API just makes it harder, right? Okay, so your development and maintenance is going to be harder than it is for a pure MPI code. Hopefully not much, but still not nothing. Okay, so OpenMP programming is, as you're probably aware, is generally easier than MPI. But it's still parallel programming. It's still hard. Getting good performance is difficult, and you need application developers with yet another skill set. So, and as you're well aware, OpenMP, as with all threaded programming, has potential problems with race conditions, non-deterministic bugs, and correctness testing can be hard. You can have non-determinism in MPI as well, but it's typically more constrained and easier to diagnose and harder to do in the first place than it is in shared memory. Okay, so what about portability? So both OpenMP and MPI themselves are really highly portable. Okay, not completely perfect, depending on which particularly if you want to use some of the more recent or more obscure features of the APIs, you might find that they are supported well by one implementation and not by another. The combination of MPI and OpenMP is slightly less portable. The main issue here is about thread safety of MPI. And as we'll talk about later, if the maximum degree of thread safety is assumed, then there is some risk that portability will be reduced because maybe not every MPI implementation supports that or supports that effectively. So it probably is desirable to try to make sure that your code functions correctly, potentially with conditional compilation, as a standalone MPI code, as well as a mixed code. And potentially, depending on use cases, maybe it's useful to have a version, to be able to generate an OpenMP only version, and conditionally compile out the MPI stuff. Next potential problem we might come across is with libraries. Okay, so if we have a pure MPI code and it uses a distributed memory library, so a library that itself uses MPI probably or some other message passing mechanism internally, then you're going to have to replace that with a hybrid version. Otherwise, you are going to be, not be able to exploit all your cores, inside calls to the library. Okay, so maybe if the library is not performance critical on the performance critical path, maybe that doesn't matter. But if that's if your library is doing significant amount of the computation for you, then you're going to want to have to replace that with a hybrid version. Such a thing may or may not exist depending on what library you're using. So some libraries simply do not have. Some libraries have MPI versions. They don't have multi-threaded versions. On the other hand, if the MPI code uses a sequential library, so it's just making, every MPI process is making separate calls to a sequential library, then you're going to either want to replace that with a threaded version of the library and call that from the OpenMP master thread, or alternatively have a thread safe version of the library that you can call from multiple threads inside parallel regions. So again, one or both of those implementations may not exist for a given library. The other problem you can sometimes run into is if you do have a threaded or hybrid library version, if those versions use something other than OpenMP threads internally, then we can end up with problems with oversubscription. Because what can happen is, if you then have two potentially competing threaded runtime libraries active in your application. So both your application, which is creating OpenMP threads, and the library, which is creating something else, maybe POSIX threads internally, then they might not play nicely with each other. Those threads may not idle nicely and release their hardware resources when they're not being used. Or you might need to take some care about whether that's happening correctly or not. Okay, let's now look at some potential reasons why performance might go wrong. So there are several things. Adding OpenMP can introduce additional overheads that aren't present in the MPI code. So things like additional synchronization, things that we talked about in the last session, false sharing, sequential sections, numer effects, communication due to numer effects, or contention for bandwidth due to numer effects, whatever. So there are things, and we'll talk about some of those in a bit more detail. If we go to hybrid MPI and OpenMP, then we're introducing a tunable parameter, which is how many OpenMP threads are we going to run per MPI process. So we have to make that choice, and the optimal value is going to will depend on the hardware, may depend on the compiler that you're using, might depend on the MPI implementation that you're using, and may also depend on the input data. It's generally speaking hard to guess the right value or the optimum value without just running some experiments. It's hard to a priori be able to say, okay, I know that that 4 OpenMP threads per MPI process is going to be optimal. How do you know? Okay. And then the other thing you potentially have to worry about, depending on how your batch system is set up and implemented, then the placement of MPI processes and their associated threads within a node can have performance consequences. So typically for the most part, if we're just using pure MPI, then in almost all cases, we simply don't care which, within a node, which MPI process is running on which core. For most applications, it makes very little difference. However, you go to MPI processes and threads, then you may well want to make sure that your OpenMP threads are all in the same numer domain as their parent MPI process, or all using the same shared level 3 cache as their parent MPI process, for example. And that may or may not be conveniently handled for you by your batch system setup, depending on how it's being done. Okay, so what can go wrong? Okay, well, it's just like with normal OpenMP, and if you do an incremental loop by loop approach, then that's relatively easy to do, but it can be difficult to cover everything, to cover all the computation. It's really just Amdahl's law argument implied inside a node. So the natural or easy way of writing OpenMP is to do it on, is to do parallel loops, and you can end up with you can quite easily end up with sequential sections of code. What else? You can end up having more synchronization than what you needed in a pure OpenMP version. Okay. If we're not going to assume that our MPI is thread safe, we'll come back to that later on. What else can go wrong? Okay, so you think about how do MPI processes synchronize with each other? Well, they do that because we have typically through the point-to-point messaging semantics. Okay, so in MPI, communication and synchronization are really quite tightly bound to each other. So MPI processes synchronize, for example, where you have a blocking receive, or you have a wait, an MPI wait, or potentially at collective communications. But in MPI, if you're doing point-to-point communication, you're also doing point-to-point synchronization. So MPI, if you're doing point-to-point communication, the MPI processes only have to wait for the processes that are actually communicating data to them. Whereas that pattern isn't easily implementable in OpenMP. Okay, so this kind of very loose thread to, one thread to thread pairwise synchronization isn't really well supported in OpenMP. You end up typically using full thread barriers to do the synchronization instead. And that can actually be more expensive. So full, especially if we're end up using a lot of threads, then full thread barriers can be more expensive than the corresponding point-to-point synchronization implied by MPI messages. When we have pure MPI, then in most applications, what happen is that when we run across multiple nodes, then some messages will be inter-node. Okay, so in other words, communicating between MPI processes on different nodes, and some will be intranode. So those are MPI processes communicating with other MPI processes on the same node. And those in the pure MPI, those two different types of messages, which will be typically handled differently by the MPI implementation, say the internode ones have to go across the network, the intranode messages are usually done in shared memory. It's perfectly natural for all those to happen at the same time, for there to be internode and intranode communication going on concurrently. With a hybrid program, it's actually harder to try and overlapping inter-thread communication with internode MPI messages is actually more difficult and less natural. We'll see why that is in a minute. Okay. So we talked about last time, OpenMP can suffer from false sharing. Okay, so this idea that you can get these cache-to-cache transfers using the cache coherency mechanism caused by multiple threads accessing different words in the same cache block. Whereas pretty much MPI never, that's never going to happen, because every MPI process has is accessing a completely separate address range and part of memory. So there's no way that can happen in MPI. And then again, so also picking up from what we talked about last time, there are numer effects. Okay, so just to recap, so nodes which have multiple sockets, and also these days, loads and chips with large core counts typically also have multiple numer domains per chip. And the operating system is allocating virtual memory pages to physical memory locations. So it has to choose a socket or a numer domain for every page. And say the common policy is first touch, so allocate on the numer domain where the first read or write came from. Okay, so remember from last time, that's absolutely the right thing for MPI, but for OpenMP, that's the worst possible thing if our data initialization is not parallelized, in which case all the data can end up on one socket. So the result of this is typically that numer effects will limit the scalability of OpenMP. So it's very common that it's advantageous to run one or at least one MPI process per numer domain rather than one MPI process per node. So that's very typically what we find for MPI plus OpenMP applications on ARCHER2. So on ARCHER2, we have every node has 2 sockets. Every socket has 64 cores. Every socket has 4 numer domains. So every group of 16 cores belongs to a different NUMA domain. There are 8 NUMA domains per node. So that usually means on ARCHER2 you want to run at least 8 MPI processes per node. And it's very rare to see cases where fewer than 8 MPI process per node is optimal for hybrid programs. It's often more, so probably 4 or maybe 8 threads per process tends to be a good choice. So it's very much dependent on the application and the data inputs, so it's difficult to tell. But it's very uncommon to have to have good performance running more than 16 threads per process. Okay, yeah. So process and thread placement. Okay, so if we have NUMA nodes, then we really want to make sure that our MPI processes are spread out across the sockets, across the NUMA domains, and the OpenMP threads are on the same NUMA domain as their parent process. On ARCHER2, the Slurm is set up so that happens by default, and so usually you don't have to worry about it. But that's not, if you move to other machines, that's not necessarily guaranteed. And even on ARCHER2, where this does get complicated or can get complicated, is if you want to exploit SMT. So if you want to use hyperthreads, you want to run more than one OpenMP thread per physical core, then that's, getting the mapping correct might not always happen. The default settings might not always do that correctly for you. So you then have to think rather carefully about your well, unfortunately, this is, the way this is controlled is a kind of messy collaboration between the batch system and the OpenMP runtime. So, you have to maybe use both batch system settings and OpenMP affinity control settings to get the right thing. So you'll see, if you look in the sort of recommended batch scripts, Slurm scripts for ARCHER2, you'll see that it sets the environment OMP places equals cores. Okay, so to make sure that that different, that by default different OpenMP threads get bound to different physical cores. So yeah, different batch systems vary, different implementations vary. So you will need, if you're running on different HPC systems, you will need to consult the local documentation about how to do this correctly. Generally recommend doing sanity checking. Okay. So there is a useful little application code which originated from Cray, and there are multiple versions around online, but it's usually called XT High. Okay, so like that. And what it does is it simply prints out the core binding for your program. Okay, so you can run the same number of, you can run it with the same number of MPI processes and OpenMP threads as you want to run for your application, and it'll print out how the batch system and the OpenMP runtime is doing the thread binding for you. So that's a good sanity check. Okay. It's actually implemented as a module on ARCHER2. So if you just do module load XT high, then you get that the executable called XT-high will be in your path, and you can just run it. So yeah, so it's a good sanity check as to whether your process and thread binding is doing what you expected or hoped for. Of course, that does rely on your application not then deciding to change the number of threads or not, internally or things like that. Okay, so Chen's asking how many OpenMP threads should be dealing with MPI communications inside an MPI thread process or whatever on a NUMA node. Okay, I'll come to that. Okay, so hopefully we'll discuss that later on. If you have any questions by the time we get to the end, then please come back to me. Okay, so that question does lead into the next topic, but does anybody else have any other questions on what we've just covered? Okay, so this is a long session, and this would be an appropriate point for us to take a short break. And so I suggest we take a break for about 5 minutes, and then I'll resume with this talking about the styles of programming after that. Okay, so now let's look at the different styles of MPI and OpenMP programming. So we can actually identify 4 different ways of doing this depending on when and how the OpenMP threads are permitted to make MPI library calls. And each potentially has its own advantages and disadvantages, which I'll try to go through. And MPI has a threading interface which allows us to request and query the level of thread support that the MPI implementation is providing. So as a brief summary before we go look into the details, these are the 4 styles. Okay, so the first one is called master only. Okay, and in this case, all the MPI communication takes place in the sequential part of the OpenMP program. So we don't do any MPI calls inside OpenMP parallel regions. The second style is called funneled. Okay, so in this case, still all the MPI communication takes place through the same thread, the master thread, but that could be inside parallel regions from thread 0 as well as outside parallel regions. The third one is serialized. So this is where we allow different threads inside a parallel region to make MPI calls, but only one at a time. And now we have some problems again, which we'll go into a bit more about. We now have to, if we have more than one thread making MPI calls, we then have to distinguish somehow between sending and receiving threads by using MPI tags or communicators to identify which which thread messages are coming from and going to. And then you have to start being rather careful about worry about race conditions on buffers, etc., etc. And then the final style is called multiple, which is basically where you can do anything. So MPI communications can be happening simultaneously inside parallel regions from more than one thread. Okay, so So main issue here is that some MPI implementations don't support that, and those which do often don't really perform very well. Okay, so just to go through each of these in a little bit more detail with some sort of sketch code. Okay, so for master only, you typically have your computations done in parallel regions or parallel loops, and then the MPI calls are made outside parallel. All the MPI calls are made outside parallel regions by the master thread. For funneled, then we allow MPI communications inside parallel regions, but we restrict those to the master thread. Okay, so we might put them in a master region here, and then probably you're going to need to, if there's computations, other computation going on inside the parallel region, then you probably need to synchronize your threads somehow. Okay, so you probably need some, you probably need a maybe not an explicit barrier, but an implicit barrier before and also after the MPI communications. So serialized, so we're allowed to call MPI from different threads. But we have to make sure it's only one at a time. There's various ways of arranging that. So one of them might be to put is to enclose all the MPI calls inside critical sections. And then for multiple, anything can happen. Okay, we can be calling different threads can be calling MPI at the same time. So what about thread safety? Well, it turns out that retrofitting, most MPI library code bases are quite old and predate the need or concept for hybrid MPI and OpenMP programs. And retrofitting thread safety into MPI libraries is difficult. And some of that is basically caused by the way that MPI is specified. So the need to have internal message queues and do message matching processes inside the MPI library means that efficient multi-threaded implementation is actually pretty hard. So MPI implementers have done a lot of work to try and improve the efficiency, but it's challenging. Okay, so you either have to do something internally, you either have to lock access to internal data structures inside the MPI library or replicate them and have a separate data structure per thread. So this adds some significant overheads which you wouldn't want if you don't need it. And MPI, okay, this is a definition of thread safety. Okay, there is no good universal definition of thread safety. What I mean in this case is it safe for multiple OpenMP threads to make concurrent calls to the MPI library? Okay. Can I have more than one thread active inside the MPI library at the same time? Okay. Without any adverse consequences on correctness. Okay. Performance is a different matter. Okay. So am I guaranteed that doing that will always give a correct result? So MPI defines various classes of thread usage, and you can ask the library to supply an appropriate implementation. So the way this works in MPI is by the function called MPI init thread. So what this does is this works in the same way as MPI init. Okay, so you would call MPI init thread instead of MPI init at the start of the MPI program. Okay. So this also does the MPI initialization, but in addition, it sets and returns the level of thread support. Okay. So in addition to the usual arguments for MPI init, we also pass in the required level of thread safety, and we get back the a pointer to the provided level. Okay. And these arguments have predefined values which are set in the which are defined in the MPI header file or MPI module or whatever. So there's 4 different levels. So that the MPI supports. So there's thread single, which says only one thread will ever execute. It says there will never be multiple threads executing inside inside an MPI process. Second one is funneled. It says the process may be multi-threaded, but only the main thread's going to make MPI calls. Okay, so that covers both the master only and funneled styles of OpenMP. Okay, so you have to recognize that these are designed to make sense for other threading models than OpenMP, where the concept of a master thread isn't necessarily as clear. And there's serialized. Okay, so that does map onto the serialized pattern. Process may be multi-threaded. Multiple threads may make MPI calls, but only one at a time. So guarantee that MPI calls are not made concurrently from 2 different threads. And then thread multiple, okay, which is the difficult one to implement, is where multiple threads can call MPI with no restrictions. So these are they're implemented as integer values and they're monotonic, so you can compare them. So they're guaranteed to be ordered. So yeah, they don't strictly map onto the 4 mixed mode styles because of the need. They're intended to support things other than OpenMP, where you don't have concepts of parallel regions and teams of threads and so on. And there's also a query thread function, okay, which just returns the. So you can call this any way you like. So this just returns the current level of thread support that the library is providing. Okay. So you can compare that. So if you call MPI init thread, then you can be defensive. If you detect that the provided level is less than what you requested, then you can exit gracefully, for example. Okay, so what are the advantages and disadvantages of these 4 different styles? Well, for master only, the big advantage is that it's relatively simple to write and maintain. You have this very clear separation between the outer and inner levels of parallelism, between the MPI parallelism and the OpenMP parallelism, and they don't interact with each other. So it means that you never have any, because all the MPI is done outside parallel regions, you have no concerns about having to synchronize threads before or after sending messages. And in practice, the majority of applications that use MPI and OpenMP are written like this. I say largely because it's just easy to do. It's the easy way to implement it. A lot of applications have their MPI communications and the computations deliberately and for very good software engineering reasons, well separated in the code structure. So you'll typically have a library or a subset of routines which are where all the communication is implemented, and so the application presents an internal interface to all the communication. So that's a very sensible software engineering design, but it makes doing anything other than master only really difficult, because you have to basically break apart that. And if you want to have computation and communication happening at the same time, then it often means you have to break apart that encapsulation somehow. Master only does have a bunch of downsides, though. It means that threads other than the master thread are idle during MPI calls. So while the master thread is doing MPI, the other threads, and therefore the other core, the other threads don't, logically don't actually exist at that point. But in particular, the cores, other cores are sitting there doing, are guaranteed to be sitting there doing nothing while the MPI calls are happening. Because MPI typically actually, when you call the MPI library, it's typically reading and writing the message, the data that's in the message buffers at some point. Then it means that all the communicated data gets cycled through the cache where the master thread is executing. So you cause cache-to-cache transfers. If some other thread has computed some data values, then and the master thread is doing the MPI communication of those data values, then you have some internal communication via the cache coherency mechanism to get that data from one cache to another. It also means, to come back to a point made earlier, that the inter-process and inter-thread communication aren't going to overlap, because they're guaranteed to be happening at separate times. The inter-thread communication can really largely only happens inside parallel regions. The inter-process communication happens outside parallel regions. So there's no way to have those going on at the same time. So the only mechanism we've got for synchronizing threads is by ending parallel regions and starting parallel regions, which has a relatively high overhead. And it also means that in this case, if we have derived data types in the MPI, which need to be packed and unpacked before the data is, packed before we send and unpack after receiving, that packing process is actually can be computationally quite expensive. So it can turn out that that packing and unpacking takes as long or even longer as the actual message transfer itself. And by restricting the restricting that to happening outside of parallel regions, it means again you can only ever devote one core for that process to packing and unpacking. Okay, so an example. Apologies, this is in Fortran, but hopefully it's simple enough to try and explain what's going on. Okay, so this is kind of a minimal, a really minimal MPI program. Okay, so I have a loop which computes some values in an array A, and then the MPI process sends the last value of A, and then receives that value from its neighbor on one side. So it sends AN and receives into A0. Okay, and then it does some computation that requires A and in particular A0 at some point on afterwards. Okay, So if we think about running that as just a very simple MPI program, you think about running that as pure MPI, then that's fine. Okay. Now let's think about what happens if we turn that into a hybrid program. Okay. So we add make both of those loops parallel with OpenMP. And then we think about, okay, well, we're going to preserve the same total global problem size. Okay, so now these effectively, what's going to happen is that and you wouldn't really write it like this, but to make it clear, because I've now got I've now got multiple threads per process. If I want to keep the problem size per core constant, then the parallel loops become longer by a factor of the number of threads. Okay. So what have we done here that could affect performance? Well, in particular, we've added an implicit barrier. We've added a full thread barrier here at the end of the parallel loop, whereas with the MPI version there were no barriers. Okay, there was just the point-to-point synchronization implied by the sends and the receives. And in the hybrid version, obviously the intranode messages, get overlapped with internode messages, but the inter-thread communication actually happens here. Okay. So this is because there are some values of I for which the corresponding value was written by a different thread here. Okay, so where we have if we just think of doing a static schedule here at the boundaries between the trunks, then we're going to get the corresponding thread communication to the MPI communication is where a thread that writes AI is a different thread that reads the corresponding value of AI minus 1 down here. Okay, so the corresponding the cache miss that implements that inter-thread communication happens during this parallel region. Okay, so in particular that doesn't happen at the same time as the MPI communication. Okay, so funneled. Okay, advantages. Well, it's still relatively simple to write and maintain. We've had to possibly, make some compromises in the way the code is implemented to allow threads inside parallel regions to execute MPI calls. There are now possibly cheaper ways to synchronize threads before and after the message transfers, and it's now possible for it's now possible for other threads to do some computing while the master's in the MPI call. It's possible to try and achieve some overlapping. Okay, and this is important because realize that yes, okay, you kind of think that, well, can't I do that in pure MPI anyway? And the answer be by using non-blocking MPI calls. And the answer is yes, but okay. So unless you have unless your MPI implementation supports an additional helper threads, then in fact most MPI libraries don't make progress. Okay, so you can do non-blocking communication, but it doesn't actually do communication at the same time as computation, because the MPI library can only really make any progress while it's inside an MPI library call. Whereas using funneled style gives you a very explicit way of having one thread inside the MPI library and other OpenMP threads doing computation at the same time. So it potentially allows you a more effective mechanism of really doing the overlapping of computation and communication. Downsides, well, we started to make a less clear separation between the levels of parallelism. We still have the problem of locality of data, so still passing anything that gets communicated has to go through the cache where the master thread's executing. We still don't really have we may not have interprocess and interthread communication overlapping properly. And it introduces this kind of awkward asymmetry between threads. Okay. Why is it awkward? It's awkward because the way that OpenMP is designed it's kind of makes your life easy. OpenMP kind of says, well, my basic model is that all the threads are doing the same thing. Okay. I mean, you don't have to, but the way OpenMP designs is it's kind of designed with that pattern in mind. Okay, where all the threads are pretty much are executing the same block of code. Okay, parallel region, all threads execute the same block of code. Parallel loops, all threads are different. Threads are executing different iterations from the same loop. Okay, but now we have to kind of explicitly distinguish between one thread that's doing communication and the other threads which aren't. So there's a couple of ways of doing that, okay, of achieving that. So one is just to use a plain old parallel region and explicitly call out the master thread. Okay, so if I'm thread 0, then do the MPI, otherwise do some computation. So that would be fine, but there's a real downside here because of the way that OpenMP is designed. In this else branch here, we have not all the threads are executing. So that means that you can't use work sharing in there. You can't use OpenMP4, you can't use OMP4 or OMP2. You can't call OMP barrier, okay, inside this else branch. So if you have a loop, you have to, you would need to explicitly, manually distribute the loop iterations between the threads. So this introduction of asymmetry is not really very nice. Okay, and you can imagine that maybe this else branch calls a bunch of different functions, and they've all got there's multiple parallel loops inside here. There can be a lot of refactoring required to change your nice OMP4 or parallel, your nice OMP4 statements into something horrible where you have to explicitly calculate loop bounds for every thread. The other option is to use nested parallelism. Okay, so the other way of doing this is to basically have an outer parallel region with 2 threads. And then one of those threads does the MPI, and then in the else branch you spawn a new parallel region, okay, with one fewer, with basically one fewer number of threads. Okay, so you have 2 threads here, so this creates 1 extra thread, and then this creates n-1 extra threads, where n's the total number of threads that you want executing. So this at least means that you can still, because this is a separate parallel region, you can use, you can use work sharing inside here absolutely fine. It's not a problem. But then say, well, actually I can't, I have to close this parallel region before I can synchronize, because there's no way, there's no way to have a barrier which includes this thread and these threads inside here. Okay. We also talked about having nested parallelism introduces some extra overheads, and also another thing which can go wrong is that this pattern can screw up the binding. Okay, and in particular this happens on I've done some experiments with this pattern on ARCHER2, and this is a problem. Okay, if you do this, then if you have nested OpenMP parallelism in a hybrid code on ARCHER2, then the thread binding all gets confused, and you end up with multiple threads executing on the same core. There is a workaround. You have to, instead of setting OMP places equals cores, you can set OMP places equals sockets, which sort of lets your threads run everywhere, and you just have to kind of cross your fingers and hope that your threads are not going to migrate around too much. It seems to work okay, but it's not a particularly satisfactory solution. I couldn't find any other way of persuading Slurm plus the OpenMP runtime to actually do the thread binding correctly with this kind of pattern. Okay, so that's funneled, which is doable but has some problems. Serialized, okay. What's the advantage of this? Well, it's now easier to make threads compute while one is an MPI core, okay. And now we can get some better locality, because we can now arrange for a thread that computes something is also able to communicate it, in some sense, okay. So we can arrange for threads to communicate their own data, in other words, the data that they're reading and writing. Downside, it's getting harder to write and maintain. Okay, we are splitting. So this goes back a little bit to what Chen was asking. Okay, when we're now splitting up the messages. So instead of sending one big message, we can end up splitting the messages into smaller pieces. So this does have actually both advantages and disadvantages. In the sense that more smaller messages, as the downside is that you incur some additional latency overheads. Okay, so every MPI message, there's a fixed latency cost for starting the message, and then a cost per byte. Typically, there's a latency plus bandwidth cost for MPI messages, and by having more smaller messages, you're increasing the latency overheads. On the other hand, if you really have very few MPI processes currently computing from a node, you may actually underuse it's possible that you might, depending on the architecture, you might underuse your network resources. It's typically not too bad. If you have multiple network connections per node, then most MPI implementations these days, if you send one big message, it will split that up into packets and multiplexes that across the different network ports. So that's sending single big messages is not a problem. The problem is that if you do that in master only mode, you're doing that and all the other cores are doing nothing at the same time. That's the big deal. You now have this problem. You need either to use tags or communicators to distinguish between messages that are coming from or going to different threads in the same MPI process. Okay, that's because MPI itself has no way to distinguish between different threads, and that's a bit painful. Okay, so because by default, a call to MPI received by any thread in an MPI process will match an incoming messages from the sender, where the sender is a different process rather than an individual thread on a different process. Okay, so to distinguish between messages intended for different threads, we can use MPI tags. Okay, but if the tags are if we're already using tags for other purposes, that gets a bit messy. You end up having to do some encoding of you have to encode both the original tag and the thread ID into the tag, and you have to then be careful that you don't run. You do tag is original tag plus very large, plus some big integer times the thread number, And then you have to be careful that you don't run out of, you don't exceed your tag space. Okay, so it's just messy. It's also possible for different threads to use different MPI communicators and to distinguish like that, which works for some patterns but not others. So your sort of classical halo swapping problem is not easy to implement like this. So it works where if thread n in one process only ever communicates with thread n, the corresponding thread in another process, then you can do it with communicators. So you can have for every thread can use a different communicator. But a lot of communication patterns don't fit that very nicely. Okay, and then finally multiple. Okay, so in principle now messages from different threads could, in theory, overlap with each other. But in practice, in order to make the MPI implementation thread safe, well, the MPI implementation is internally serializing them. Okay, there's some lock inside the MPI library that means that those sends and receives get serialized anyway. Okay, so it doesn't really help in that sense. But it's now more natural for threads to communicate their own data, so you get better locality properties. And actually now you have fewer concerns about synchronizing threads because we've passed the responsibility for doing that into the MPI library. So instead of serialized, where it's our responsibility to make sure that MPI calls don't come concurrently from different threads, we're now basically passing that problem into the MPI library to deal with it. But that responsibility comes with overheads inside the library. Downside, this is not easy to write. Okay, we've now got a very tight integration between the different levels of parallelism. I have to care about, to make sure that everything is, all our accesses, multi-threaded accesses to message buffers, make sure everything's correctly synchronized and so on. As I said, well, most common MPI implementations do support this. Sometimes you have to enable it with with an environment variable or something like that. A lot of MPI implementations don't support it by default because of the extra overheads involved. You have to do something to turn it on, and implementations don't necessarily perform well like that because there's a lot of, it forces it into doing a lot of additional synchronization that it wouldn't otherwise need to do. Okay, so summarize, this is actually becoming pretty standard practice. A lot of applications do it. I say, back in the days of Archer, before ARCHER2, we did a study on this, and even then, it was something like, it's a bit of an approximation, but something like 30% of the consumed CPU hours were coming from hybrid codes rather than pure MPI. So it's very common practice, but it just makes your life harder. Okay, so it gives you additional correctness, potentially additional correctness problems unless you do master only. Gives you additional performance problems, and then you have these additional concerns about choosing the number of threads per process and making sure your thread and process placement on NUMA architectures is done correctly. Okay, that's the end of my slides. Does anybody have any questions? Okay, I guess I should also say that doing performance analysis and performance tuning on hybrid codes is actually quite difficult. There are a lot of competing overheads to understand. There are lots of different trade-offs going on when you change. As you change the number of OpenMP threads per process. So some things as you do that, so some overheads will increase, other overheads will decrease, and some of those overheads interact with each other. So you know, trying to analyze the performance and work out what's going on it is quite difficult. So yeah, some profiling tools are helpful. So I particularly like using Scholastica for doing this, provided you can get it to work with your application. That's unfortunately it's a it's more than a bit fragile in terms of actually getting it to build with applications. But if you can get it to work, then it tells you a lot about what's going on with all the different overheads. And you can figure out how those overheads, you can get some good information about how those overheads are changing and interacting with each other as you vary the number of threads per process. But in practice, I think what a lot of application developers do is that they do something, use master only. So I'll do something reasonable. Just to make sure that you're covering that most of the expensive parts of the computation are OpenMP parallel, and then just suck it and see. Okay, and then you just basically say, okay, then I'll just go with whatever number of threads per process works best, and and not really dig too deeply into the reasons why. Okay. Thank you very much, everybody. So for our final session on Thursday, we'll be looking at the OpenMP memory model and also a bunch of sort of more esoteric and recent features that are available in OpenMP. And hope to see you online then.